couple months back, I took a train from DC to New York, and as I was making this trip, I decided to track the train's movement with my phone's fitness tracker app. The app allowed me to download what's called a GPX file containing the tracked data. Out of curiosity, I decided to download this file and see what's inside. As it turns out, a GPX file is actually an XML file that uses a schema defined by the schema location link at the top here. We can see the breakdown of this file here. We have a track, and a track is comprised of multiple track segments, and a track segment is comprised of multiple track points. And a track point consists of lat, long, elevation, and a timestamp for each point. And what this simple parser is doing is just going through all the track segments, and it's taking all the points and just putting them in a pandas data frame. Now that we have a basic GPX file parser written up, we're going to be doing the data analysis portion in Jupyter Notebook. I've imported some libraries I'll be needing, as well as the GPX parser that I just wrote here. We are also going to be using Plotly to visualize the data. Since the GPX file gives us lat, long, and elevation, that's the first thing I'm going to visualize. I'm going to first print some high-level information about the data with the file object, just to make sure things from a top level look okay. Here we see the plot of elevation versus coordinates on a map, and this shows us the path the train took from DC to New York. At first glance, things look okay, but as I hovered over the line, I saw that the elevation numbers were not quite what I expected. Much of the elevation numbers were negative, and this makes me a little suspicious that the app didn't do a great job of measuring this data. A 3D plot of elevation versus lat and long confirms that most of the elevation numbers are actually probably not good. You can see just how much of the line actually goes below zero. So AELE is the elevation, and you can see a whole bunch of these numbers all fall below zero. And so, if the train's on land, this is not really possible. So we're kind of forced to conclude that these elevation numbers are probably no good. You can see as the train was traveling from DC, its starting point, to New York City, its ending point, a lot of these numbers are just negative. So we're going to ignore these elevation numbers from here on out. Next, I wanted to see where the train was traveling the fastest. This means we need to derive the velocity of the train from our data. Fortunately, we have the numbers we need here to do so. The distance between successive coordinates will give us our incremental distance, and the time displacement between data points will give us our incremental elapsed time. Divide the delta of the distance by the elapsed time, and you'll get the instantaneous velocity at each coordinate point. With the help of some online resources posted in the references section of this notebook, I wrote what's called the Haberstein formula, used for calculating the distance between lat and long, taking into account the curvature of the Earth. With some additional pandas foo, I derived the metrics I need and added them as columns in the data frame. When I run the describe function on the data frame, I noticed some interesting points. The mean velocity was about 77 miles per hour, with max velocity reaching up to 142 miles per hour. Now, I actually doubt that this was the true max velocity. I think the real number was more around 120 miles per hour. Again, this is possibly due to tracking errors with the fitness app. Alright, now let's move on to actually plot the velocity we just computed. Cool. Now it's possible to see where the train was going the fastest. In green, which level here, where it was going at a moderate speed in yellow, and where it was going the slowest in red. This line here is also a plot of the same data, just not really color coded. It's just simply a 3D plot. But here you can actually see the path of the train because I am plotting lat and long as x and y. Yeah, I'm color coding my colors here. So yeah, this is interesting. You can see there are several points where it was actually going really fast, and other points where it was just going at a moderate speed. Also, just out of curiosity, I also wanted to see what the most prevalent speeds were, so I also generated a histogram of the velocities. With the number of bins being 20. And this showed me a bimodal distribution. I guess this makes sense because the train can take a long time to slow down for an intermediate stop, given that all other times it's traveling fast. And you can see, yeah, this is the most prevalent speed, which is, I guess, 110 miles an hour. It seems reasonable. As mentioned earlier, I put the references I use at the bottom here. One thing I do want to point out is that certain GPX files, like the one I downloaded from the app, are actually corrupt in that they use a metadate tag. If you hear, it says metadate, right? That's actually wrong. It's actually supposed to be metadata as per the official schema. But it is still possible to parse these files, as we've just seen. I hope this was interesting to you as it was to me, or that you've learned something from it. If you want a copy of the code, I've posted the parser and the notebook to GitHub, which you can access via the link in the description. And with that, we conclude this investigation. Thanks, and see you in the next one.